All right, good afternoon, everybody. I'm really pleased to be able to introduce Robin Hogan today, our CCS seminar. Robin comes to us from ECMWF, that's the European Center for Medium Range Weather Forecasting. Prior to that, he was a professor at the University of Reading, where I think you still hold a position, right? And he's really kind of a polymath in the areas of radiation, remote sensing, particularly with active instruments, radars and lidars, both from the ground and space. Has made really fundamental contributions in how we do synergistic retrievals of cloud and precipitation properties, including developing new and influential techniques for deriving scattering properties of complex hydrometeors. So really a wonderful person to talk to about anything related to radiation and remote sensing. And he's out here because just 2 days ago, we had the successful launch of the EarthCARE mission from Vandenberg. Congratulations.
Don't clap me.
It's been a long time coming. And so we're all really excited about that. We're pleased and excited to see the data that will be flowing here soon. And he's going to tell us about what we're going to do with EarthCARE here today, and I'm excited to hear about it. So with that, I'll hand it over to you, Robin. And one more thing, a technical thing. So if you're online and if you're having trouble with the video feed, apparently if your video feed is getting cropped, you need to right-click on the video and then select fill frame. So if your video is getting cropped, right-click on the video and select fill frame if you're online. All right, take it away, Robin. Thanks.
Okay, thanks ever so much, Matt, for that very kind introduction. So yeah, it's a pleasure to be here. Thanks ever so much for the invitation. I'm at the birthplace of CloudSat, so I think this is a great opportunity to tell you about EarthCARE. And what we're going to do with it. Now, really, I'm posing this as a question because EarthCARE has promised lots of things. It's got all these instruments I'll talk about, great capabilities. We promised to solve the climate sensitivity problem, right? So you think, oh gosh, it's in orbit now. How are we actually going to do that? So there's lots of things where I really appreciate your feedback, your ideas on what we can do with this satellite that we haven't thought of so far. So I'm going to show you, well, let's just start with what the launch looked like. So it was a bit of a cloudy day, unfortunately. So the launch site, you can just about above, so we've got here Anthony Illingworth, who's the father of EarthCARE, thought up the idea in the 90s, but then, of course, a huge team of Europeans, Canadians, and Japanese have worked towards the satellite. This is Hajime Okamoto, who's the co-chair of the Mission Advisory Group, along with myself, who's the European co-chair. And in this tower here, you've got CloudSat on the top of a Falcon 9 rocket. Obviously, rocket launch. This is our celebrating afterwards. That's Director General of the of ECMWF, Florence Rabier. That's the moment where EarthCARE was deployed from the Falcon 9 before it came. Before it deployed from the second stage. The first stage obviously came back, and I thought this is probably the best. Oops, this is the best. If I press the right button, this is the best thing. A tight composite time lapse showing the rocket taking off and the booster returning. Oh, that's pretty amazing. So somebody on Twitter let me show that to you. So let's move on. So an overview. I'm going to talk a bit about the original motivation of the project, cloud feedbacks. Then I'll talk about what EarthCARE is, some of the satellites, some of the instruments that we have on it. A bit of background on particularly the ECMWF perspectives. There's really quite a few ways in which CloudSat and Calypso have been useful to us and, of course, to the wider community. I mean, thousands of papers have come out of this. So I obviously need to explain to you what I think the benefits of EarthCARE, how this is going to be a big step up in terms of capabilities of measuring clouds and aerosols is concerned. What have we got next? I'll talk a bit about the retrieval side and some of the new things that we're going to do. I'm focusing on my own work, which, as Matt said, was on synergistic retrievals, where we're combining the instruments to get the best estimates of the properties of clouds, aerosols, and precipitation, and particularly how we get to radiative closure, so a description of the atmosphere, the clouds and aerosols, and so on. And because we're observing the broadband fluxes at the same time on the same platform, we can check that the retrievals, when fed into a radiation scheme, give us the fluxes that we measure, and then this gives us confidence in the retrievals for using them to, check climate models and the radiative impacts of those clouds. So that's a key aspect of the mission. A bit about 3D radiation, and then some of the new things that we've done more recently, which are going to be key to the mission. So some of the aerosol work with the Aeolus satellite, which is a high spectral resolution lidar launched by the European Space Agency for winds. And you can also derive new aerosol distributions that we wouldn't be able to do with something like Calypso. We're going to assimilate EarthCARE into our weather forecast model, and we've demonstrated this with CloudSat and Calypso. Of course, that wasn't available in real time, but the same process applies. And some of the other ways in which we want to tackle, evaluating models. One of the, you have to say, well, we've delayed this launch so long. Is any of the science still relevant? Well, of course, it still is. But a new range of scientific opportunities have emerged in the last 20 years. And one of them is high-resolution global models are now sort of a common thing. There's quite a few of them now. And those models, although they maybe don't need a convection scheme, they still need to be evaluated. And we now have observations at the same scale that they're modeling. And so this is a kind of opportunity now. We've got better models, but we still need to evaluate them. And a key thing I want to get out of this seminar is to try and encourage collaboration across continents. And the one opportunity for this is what's called the MAP. I'll tell you about the acronym later, but it's basically a shared computational resource where the data from the A-Train and also EarthCARE would be available. So anything that is doing longer-term statistics using both, applying the same algorithms to both data sets, could be use this computational resource, which would make it much easier for collaboration. So this is a plot you have seen, of course, many times. The projected temperature is looking really bad. We have most of the trajectory we're going to be on until the end of the century is in our hands, and depending on our emissions. But then within any given emission scenario, there's a large uncertainty, most of which is due to clouds. And then if we kind of give up on net zero, then we might be in a trajectory like this, but we could have between 3 or 5 degrees of warming. So climate sensitivity is the uncertain factor, but cloud feedbacks is the largest single component of this uncertainty. And the question is, of course, how can EarthCARE improve this uncertainty here? And of course, it's not just the global mean that's important. There's large uncertainties in regional climate change, and forecasts like the dry areas will get drier have obviously got profound impacts for human civilization in certain parts of the world, agriculture and so on. But as you go to smaller and smaller scales, the quality of your climate predictions is much less certain. So improving climate models and also weather models in general is incredibly important for humanity. And then this, EarthCARE has got a great opportunity to be able to do that, but we need to think about carefully how we do this. So this is a very nice paper from Zelinka, decomposing some of those cloud feedbacks, and we can look at what progress has been made and if we can understand the processes. This is splitting the overall cloud feedback into 4, and of course you can do it more finely if you wish, but this is very useful, I think. So the low amount, as in the fractional coverage of low clouds, particularly over marine areas, is the one that's been a bit stubborn and is quite difficult to explain exactly what the mechanism is. Many models say that area will reduce, so that is acting as an amplifier because you reflect less sunlight to space. But it depends on things like inversion strength, SSTs. If you increase greenhouse gases aloft, then you get more emission downwards, so the ability of the cloud tops to cool to space is reduced. And then, of course, the aerosol impacts on clouds are very important. And this might mean that there's a dependence on the distribution due to sort of dynamical changes of the inversion strength, which is affected by the subsidence velocities in the mid-troposphere. So this is a really tough one that we really want to work on. Land cover is a bit more straightforward because land is warming faster than oceans, but most of the water vapor is coming from evaporation over the oceans. The relative humidity on average is expected to decrease over the land, and that would reduce cloud cover, even though the amount of rainfall would go up. So that tells you why you would get more intense rainfall under climate change. High altitude clouds, I mean, this is a very interesting one where in the last few years we're actually detecting an increase in the heights of the cloud tops as the tropopause raises under climate change, and most models capture this and we can now observe it. Mark has obviously done this with MODIS and CloudSat, and we can see it in Calypso as well. So this is a really interesting where we can actually see this. And one area where the Calypso measurements have been instrumental actually is to reduce uncertainty in this negative feedback. They call it the lower opacity, whereas I would think of it as a cloud phase feedback where as you warm the climate, some of the ice clouds will become liquid. When we compare two generations of CMIP model cycles and we plot the cloud feedback as a function of latitude, you can see in the blue is the CMIP 5 and in the orange is CMIP 6. And in that period, the cloud feedbacks have become more positive. And this is really because we've observed that the current clouds have got much more supercooled liquid in than the models at the time had. And in those days, many models had just a single prognostic cloud water content that was then distributed between liquid or ice according to the temperature. Nowadays, more models would have a separate variable for liquid and ice, and that means you can capture the fact that, particularly in the boundary layer, even if it's sub-zero, you've got enough turbulence to generate liquid cloud. And so I'll show some observations from Calypso where this has informed our own model. This has meant that cloud feedback's more positive. And then finally, some of the other Calypso's also been useful to constrain the anvil feedback. I mean, there was a lot of talk about the iris effects, but that's basically been disproven. And we can put bounds on, although there's a correlation here, the actual amplitude of this sort of shrinking anvil effect on climate is believed to be very small now, and Calypso's helped in constraining that. So, what is EarthCARE going to do? It's going to measure clouds, aerosols, precipitation, radiation with its 4 instruments that I'll go into a bit in a moment. We have a cloud radar and cloud lidar. So the radar is directly down and the lidar slightly off, 3 degrees off to avoid specular reflection from ice particles. The radar has a Doppler capability. So that's the big new thing for the radar, and the lidar has a high spectral resolution capability, and this gives it the ability to measure the particle and the scattering from the air at the same time. And if you can measure the scattering contribution from the air as you go down, even through clouds, you can infer what the optical depth is, or more particularly the extinction coefficient as a function of height. So you've got much more precise measurements of the radiative properties of the clouds that you need. We've also got a imager in the visible, near-infrared and thermal infrared, giving us a bit of context, and also a 3-view broadband radiometer, so like Ceres, but measuring at 55 degrees fore and aft, and another one at nadir. So better measurements of the fluxes. Of course, we don't measure fluxes directly, but if we measure at more than one angle, then you can, we don't measure at all possible angles, but with 3, we can get a much better handle on the overall flux that we want. So this is those 4 instruments separately, the radar, the lidar, the multi-spectral imager, and the broadband radiometer. And then if you're interested in the instrumental aspects, you can see where they are on the satellite. So we've got a streamlined satellite because we're in a low orbit and we want to minimize drag. We've got the large 2.5 meter antenna of the radar that was deployed just last night, I think. It's launched with explosives to fire it out, apparently, so a bit of a risky operation. I'm glad to see that that's gone well. The lidar has got 2 lasers and 1 large receiving mirror, and then you can see the smaller instruments, the broadband radiometer, and there's a forward and aft view here and a nadir view there, and the multi-spectral imager here. I don't know, I'm not quite sure what that bit is that's looking backwards. I'm sure it looks downwards, but I'm not an instrument expert. And then you've got this, the whole thing is 17 meters because you've got this massive solar array sticking out the back. Okay, so kind of impressive thing. So how does it compare to the A-train? This is a sort of summary. EarthCARE is developed by, of course, the European Space Agency and the Japanese Space Agency, ESA-JAXA. It's got the advantage of being on a single platform. It is in a lower orbit, and that's giving it something like 5-6 dB extra sensitivity, about a factor of 4 on the radar. It has the Doppler capability, so it measures full speeds, and a high spectral resolution lidar capability. It's actually in the UV rather than in the green and the near infrared, so it's a bit different. MSI is a bit like a poor man's mode. It's slightly lower spec actually, and certainly it's got 150 kilometer swath, so it's certainly narrower. But the broadband radiometer's got this advantage of 3 views. So let me just summarize how we've used CloudSat and Calypso for ECMWF, and this just a small highlight of the ways in which models have benefited from CloudSat and Calypso. You can show from CloudSat that the ice water measurements show that we really needed to include the snow in the model, in the radiation scheme, and that was an improvement that was made early on. There's Graham Stevens' dreary paper. I can't remember the full title. It's about the dreary state of low clouds, I think. Oh, that's right. It's about drizzle occurrence in a marine stratocumulus, showing that rain occurs more often than it should do in many models. And that has informed our development of our low cloud parameterizations in our model. We compared the ice-water content distributions. This was actually using our own radar lidar retrievals applied to CloudSat and Calypso from Julien Delanoë. And this is the observed distribution of ice-water content as a function of temperature. And then you can see at the time we had a diagnostic cloud fraction, I think, and then we moved to more variables being prognostic. And that led to a better agreement. I mean, it's obviously way from being perfect, but it's certainly better. It didn't have this cut-off here. We looked at forward modeling reflectivity. It was a very big thing about 10 years ago, comparing in observation space, and we certainly learnt a lot from that. We've also used the Calypso measurements for evaluating our air quality forecast. CAMS is the Copernicus Atmosphere Monitoring Service, which is basically air quality forecasts using the ECMWF model, where we have like 15 aerosol species that are prognostic. And even more here, we've got the mixed phase clouds treatments that was informed by Calypso. This is making a little bit more of a point of that one I was making earlier. This is the observed cloud phase in a particular slice going down over towards Antarctica. So this is the kind of low-level boundary layer cloud below zero, though. You see here the 0 degree isotherm hits the ground. And our model before had a lot of this cloud was purely ice. You can see there, and a little bit of liquid here, but we realized from the Calypso measurements that clearly almost all of these clouds need to have liquid at the top. And so a better treatment here puts those liquid clouds at the top, and this has a big impact in the reflected shortwave radiation biases versus series in our model. That was the error before. You can see we're not nearly reflective enough, and the new scheme is much better. And many other climate models have made changes that have improved things as well. So that was very handy, because obviously when you make cloud into liquid, there's many more numerous small droplets for the same amount of total water, condensed water, and that makes it more reflective. And we've also, yes, there's a few other things here. So we've also used CloudSat and Calypso to be assimilated into the model. And that's what we're going to do in real time when EarthCARE is launched. So we have a very complicated product chain. The color coordination is showing the instruments. So the advantage of designing the whole thing together is that you can integrate everything. And so we have our radar, lidar, imager, and broadband radiometer raw measurements. They get converted to processed measurements, but still in observational variable space. We then have the retrieved products, and the colors represent retrievals just using a single instrument. But then, of course, what I'm particularly interested in is when we combine them together. So here we've got our let me just show you what we've got over here. So we firstly do a classification of the scene. We then retrieve all the properties of clouds and aerosols together by combining the instruments, and we then do radiative transfer on the retrieved atmospheric properties, And then finally, we have a product where we compare it with the broadband measurements that are sort of coming from these arrows here. So we can have in a single product, and I should say it uses 3D radiative transfer everywhere. We reckon we can just about afford to do 3D radiative transfer with the Monte Carlo model from Howard Barker to then compare to the actual measurements. And so this is on-board radiative closure evaluation. Okay, so pretty cool. So talk a bit about microphysical capabilities. So these are the new things compared to CloudSat and Calypso. So for aerosols, we've got the high spectral resolution, and we can get aerosol type and unambiguously get aerosol extinction coefficient rather than having to use an assumed backscatter to extinction ratio, which is the kind of basic method from Calypso. We can use that high spectral resolution capability of the lidar to get the cloud extinction at cloud top of liquid clouds. I'll show a bit more about some of these details in a moment, but let me see. The radar's more sensitive, so you can do radar-lidar synergy closer to cloud top in ice clouds. And having the Doppler capability is very useful for both snow and rain. So you get one extra piece of information. So with snow, there's an uncertainty on the density of ice. And particularly if you get riming, the ice particles get denser, they fall faster, and so you can infer their density from the Doppler measurements in principle. And likewise then for radar, for rain, if you've just got the reflectivity, you don't know the size. You know, some rain, for a given rain rate, can be big or small drops, and so we can now have some information on the differences there. And again, I'll show some examples. So I'm going to focus, as I said, on this ACM CAP product. So this is the combined it's all acronyms. It's acronyms of acronyms. I do apologize, but basically it's the cloud aerosols and precipitation from combining the radar, the lidar, and the imager. And it can be applied to an arbitrary combination of ground-based or satellite instruments. So we've been able to test it on airborne and ground-based observation platforms. It uses a variational technique, so quite similar to what's used now in the CloudSat retrievals. And we've got 4 models for the radar and the lidar, which includes multiple scattering. And we also forward model the Doppler velocity, the path integrated radar attenuation. So that's where you use the surface return to get the total attenuation of the atmosphere at 94 gigahertz, as well as forward modeling the infrared and the solar radiances. So we've had so much time waiting for this satellite, right? So we're saying, oh, we need some fake data. So we've generated some simulated EarthCARE scenes using our best knowledge and very slow and accurate forward models with Monte Carlo and all that. And that's been done by taking simulations from the 250-meter GEM model. It's a Canadian cloud resolving model. And we've then run, sorry, am I pressing the wrong button? Yeah, again. We've run these observation simulators, and there's a special issue that's describing all of the retrieval algorithms. There's like a paper per retrieval. And what's unifying this special issue is that we all use, or almost all use, this common set of test data. And it's simulating the observations, including noise. Let me show you what that looks like. So if we take a swath of the imager for 6,000 kilometers, we're splitting a single orbit into 8 frames. That's how the data are going to appear to users. And in this case, we call this the Halifax scene, because it goes over Halifax in Nova Scotia. The lidar, and using the Calypso color scale, would look like this. So we've got this is Antarctica, and then this is more Caribbean. You've got aerosols, ice clouds, and then this is a super-cooled cloud with snow falling out of it. And then the new thing here is the Rayleigh channel of the high spectral resolution lidar. So what this is showing is that when you have particles in the atmosphere, you're measuring the backscatter from the air, and that means that will be attenuated by the clouds, but you won't see the cloud particles themselves. So you can do the gradient, vertical gradient of this quantity is basically proportional to the extinction coefficient. And in principle, it's unambiguous. The only issue is it's a bit noisy. So we have to, account for the noise in our processing. But that's the key new measurement here. And then on the radar, the new measurement is the Doppler velocity. Now, the raw measurements, We've yet to see, obviously it'll be incredibly nerve-wracking but also exciting to turn on the radar and see how good the radar velocities are. It's a bit marginal because the satellite's moving a lot and that gives you a lot of Doppler spread, and it's dependent quite a lot on the pulse repetition frequency. You want it as high as possible to get accurate Doppler. So we may have to average horizontally, but you can see immediately where the rain and the snow is, and this is measurements we haven't had globally ever before, so it will be very, very useful. So let me show you what we might get from aerosols. So this is, in the case of this simulated scene, of course, we have the true aerosol extinction, and we can then compare to what we retrieve. So one of the challenges in this particular case is it's marine aerosol in which cumulus clouds are embedded. And so we first have to sort of screen those out. And in this case, the retrieved extinction looks like this. So there's a certain amount of noise in this sort of first go. The integrated extinction, or the optical depth, agrees quite well on average, though we're probably a bit too noisy, are in the commissioning phase. So the first 6 months after launch, we're clearly going to have to refine the retrievals. We'll have all the calibration validation campaigns, aircraft measurements, and so that'll be a key time to try and improve some of the implied errors that we have here. Let me talk a bit about aerosol type, though, and this is one of the really cool things we'll have from the high spectral resolution LiDAR. So we measure depolarization. Of course, Calypso does as well, and this tells you something about the sphericity. So a spherical particle doesn't depolarize, whereas so if it's like it got liquid in it, then it will be spherical, but it's a dry particle like dust or soot does depolarize, well, mainly dust. But you can then combine it with the LiDAR ratio. So this is the ratio of extinction to backscatter. So that's something you get from the extinction here, and you also measure how much is backscattering. And then in this 2D space, you have information on the type of the particle. And so in this particular case, we run the retrieval of type on this is aerosol over the Caribbean, and it successfully distinguished the sea salt layer from the continental pollution. And there's not a prior information saying it should be this according to location around the world. It's done it purely from the measurements. So that'll be very useful for sort of layers in different parts of the world where it's ambiguous just from backscatter what the type of the aerosol is. And of course, for radiative impact, some of these aerosols absorb sunlight and some more reflect it. So for its impact on climate, it's crucial. Okay, busy slide. So now I'm going to talk about the retrievals from of clouds and precipitation from the combined synergistic retrieval. So what have I got here? I've got the true quantities in the top. So we've got true ice water content, liquid water content, and rain rates. In this, this is zooming in on that same Halifax scene. So we've got a sort of quite heavy rain situation over here, and you can see the ice is quite strongly. There's a lot of ice above that, and then there's a case with super cool water here. I think that's the 0 degree ice. Oh no, it's 1 kilometer. Sorry, yeah. You can see the melting layer there at about 2 and a bit kilometers. So this is clearly super cooled. And then this is our retrieval of ice, liquid, and rain, and kind of looks okay. And we can also do a comparison of true and retrieved quantities at particular heights. And I'm showing here the ice water content at a particular height and then the ice water path. And so they agree pretty well. This is just demonstrating one of the capabilities of the synergy that you might not have expected. I'm showing here the results of 2 retrievals here, and I'm showing the liquid water path through this entire profile. The red, so the black is the truth from the original simulated original model. The red is the retrieval if you only include liquid in your profile where the LiDAR would see it, and that would be the traditional thing, because you don't know if you just have radar, you don't really know if there's liquid because the return is dominated by the big particles. But what you typically find, at least in this model and in many models, is that within rain, so there's a load of rain here, there's actually some liquid water. You can see in this rainy region there's liquid water. The LiDAR's attenuated way above. And if we instead assume that whenever there's liquid, whenever there's rain, there's also some liquid water cloud. So we allow the retrieval to to retrieve liquid water, we don't exactly know where it is in heights, but we have like a simple representation that maybe has, in this case, a triangular distribution. Then when we run the retrieval, we can get a much better liquid water path. Now you might say, well, how is the liquid constrained? Because the active sensors don't see it. This is where the synergy comes in, because the path integrated attenuation tells you the total attenuation and radar wavelengths, which is affected by rain and liquid cloud. And then the rain, the other thing we have is the solar radiances. So when the sun is out, that gives you something like the total optical depth, but that's almost all dominated by the liquid and ice in the profiles. And so the combination of the path integrated attenuation and the solar reflectances enables you to distinguish what part of the attenuation was due to liquid cloud, and you can get that out. And so therefore you get better rain rates. You can see the blue line with the assumed liquid in the cloud, in the rain, agrees better with the model truth. And so you've got the strange thing where I've added solar radiances, I'm getting better rain rates, but it's by the sort of cascade of everything having to fit together with the proper synergistic use of the data. So that's something quite nice, and then this is a comparison then of ice-water path in a scatter plot when we use just the radar, so this would be like a CloudSat only type retrieval, versus when we use the radar and the lidar, and you can see it's quite a bit tighter. So let me move on now. The other thing, so now let's think about those two ways in which the extra measurements can give us more accurate microphysics. So firstly on rain. So I'm going to show you two very contrasting rain situations observed with the NASA ER2 aircraft, which has something quite like a EarthCARE platform. We've got a 94 gigahertz radar, a lidar, and we've also got a 10 gigahertz radar, which we don't use in the retrievals, but we forward model it afterwards as a form of validation. Okay? So these are the observations in a case where you've got rain caused by melting ice. So you've got the ice, and then it goes through the melting layer and it forms rain. This is the full speed and the path integrated attenuation. Okay? Now let's look at a different situation with quite similar rain rates between maybe 2 and 10 millimeters an hour. This is a case where we've got rain that's formed from collision and coalescence in liquid clouds. Okay, so you can't see a melting layer here. And in this situation, the Doppler velocity is much less, even though the reflectivity is about the same. Okay, and there's differences in path integrated attenuation. Now, when we run our retrieval on this, just to show that the full speeds are 4.5 meters a second versus 1.5. On the retrievals, and we can estimate the drop size. You can see here it's about 1.5 millimeters in this rain here, whereas here it's much more drizzle-like, and it's more like half a millimeter drop size, so much more drizzly. And what I'm showing are three different retrievals. One where we use the reflectivity in the PIA, so that's like CloudSat, just the reflectivity and the velocities, but then if we have the velocities, the path integrated attenuation and the reflectivity. What this highlights really is that the same reflectivity can give you very different drop sizes for about the same rain rate. So and this is important for representing rain processes in models, because almost all models have this, rain is rain, right? It just falls out at the same speed. But actually it's not, and it depends where it comes from. So you might think, well, I need a double moment scheme in my model, or I need a separate variable for drizzle and rain formed from melting ice. We need to address this because it affects the lifetime of a cloud. It's kind of fundamental for cloud evolution. So this information hopefully will be useful once we get the real data coming through with the Doppler. That's just to highlight the differences there. So I will now talk a bit about what we could do with snow with the velocity information. So what I'm showing here is, in the colors here, are the full speeds you would expect for ice, that'd be different types of ice, but I'm going to basically show, imagining you have particles increasing in size here. Now, a traditional assumption is that small particles of ice are solid ice, so the ratio of ice in an enclosing volume, the ratio of ice to the total volume is 1. and then they get less and they get more sort of fluffy, and more air is included in them as they get larger. That's the sort of unrhymed aggregates assumption, and typically you assume the density of those things decreases such that they become quite low density compared with a solid ice sphere of the same sort of overall envelope. Now, what happens when you get rhyming or intense rapid vapor deposition is that ice particles tend to be denser for the same size. And our assumption is that the relationship then has this linear relationship in a log scale of ice fraction up to a possible, totally solid ice. This would be like very dense hailstones. So we're retrieving a number, this density factor that expresses what the gradient is here. Now, of course, most people think of a mass-size relationship as that mass is A times size to the power of B. But when you plot all the different models that have been proposed that we could find in the literature, so this is the prefactor A and the exponent B, they tend to fall along a line. So that implies there's 1 degree of freedom, to a good approximation, where my low-density aggregates are here, and my solid ice is here, and I'm retrieving a number that basically moves me along this line to denser and denser particles. And you can see from the velocities in the colours underneath, you've got information on that from the measurements to tell you where we are there. So let's move on. So this is a case from Finland where we're looking up. We've got 94 gigahertz radar, reflectivity and velocity. This is just to show a high spectral resolution lidar to show where the cloud base is really, just because it was there. We're retrieving here snow rates and ice average size, median diameter, and then this is the density factor that we retrieve. So what's kind of interesting is that in the high clouds, the density factor is 0. That means that we've got fluffy aggregates, not much rhyming or rapid deposition going on, which you would only get when you have supercooled liquid present. But then in the boundary layer, you've got, sorry, pressing the wrong button again. In the boundary layer, it's quite turbulent, so and warmer, of course, so you're generating supercooled water. That means that the air is supersaturated with respect to ice, so you get more rapid deposition, which leads to sort of more pristine-like forms like plates, which tend to be denser than aggregates. And also you could as well get rhyming, of course. Now, how good is that? Well, fortunately, this site in Finland, Hiatila, there's surface measurements of all the quantities you could possibly want of the snow. And we were able to compare some of these quantities. Now, this really highlighted that the ideal combination of instruments would include a 35 gigahertz radar as well as a 94, because there's more uncertainties in this case than we really have measurements of, because the size is uncertain. In this case, we think we're probably below where a lidar would be able to penetrate. So the EarthCARE-like retrieval is the reflectivity at 94, the green line with the velocity here. So there's some distinction between, the black line is the observed density, some measure of the bulk density. The best combination, yes, was this blue line. That blue line matches the observed quantities in each of these much better. But we want to take the idea and try and refine it once we're in space. And what's particularly interesting from a microphysical point of view is when you compare the rhyming factor, the density factor in black, with the liquid water path in blue, you see a pretty good sort of one tracks the other quite nicely. So microphysically, denser particles correspond to supercooled water in the profile. And this is telling us things we can use to evaluate models in principle. So what we really want to do is evaluate the radiation in the in climate models, and we're going to do this by feeding the retrievals into a construction algorithm which uses the imager to give us the context, but then we can take a retrieve profile from the narrow curtain of observations from the radar and lidar and put it, we find that the retrieve profile that matches the radiances most closely, and then sort of place it there to reconstruct a 3D representation of the scene. It's only going to be sort of 20 kilometers wide roughly. But from that we can then do the radiative transfer, and we're going to do that in 1D and 3 dimensions. So this is the long wave heating rate, and then this is the reflectance if you have a 1D model versus a 3D model, of course, you can see more structure there. And then we will be able to do a closure comparison compared to what was actually measured at the top of atmosphere. And then there is still, of course, dependence of our retrievals on some assumptions. And so part of the process in the commissioning phase is going to be saying, well, we haven't got quite our assumptions right. We can tell from the radiative closure that we've got our prior ice density, or goodness knows what, wrong. And that will be refined a bit, and then we'll have products that are hopefully consistent. And this, we want to iterate this in subsequent versions to refine our assumptions. But this is kind of the core data set coming out of the mission. And we've already done this kind of thing with CloudSat and Calypso, and other people have too, but where you have, this is just for, I think it's a full orbit perhaps. We have ice and liquid water contents from a full orbit of data. We compare with the shortwave and long wave. So we've got ECRAD, that's my radiation scheme, fed with the synergistic retrievals versus the series observations. That's the shortwave, that's the long wave for a full orbit. And then we can do a scatter plot for different cloud types. And you can see certain cloud, this is for ice clouds, mixed phase clouds, and liquid. And as you might imagine, the short wave, in this case, of course, we're not doing the full 3D, so there's still quite a bit of scatter that's probably related to retrieval errors, but also the radiation. So we'll have the 3D radiative transfer in EarthCARE, and we will hope to refine our retrievals to try and narrow this down. One thing I've been working on recently that might be of interest to some is trying to work towards fully 3D retrievals, because even if we use 3D radiation, if we use solar radiances but we don't account for 3D effects, we're not interpreting them correctly. And so we kind of need a cheap way to represent exchange of radiation between columns. So this is something I've been working on. And the idea is that you do a normal two-stream calculation where you would just treat each column separately, except that you allow some exchange of radiation. I shouldn't touch the microphone there. So, for example, the solar radiation comes down at an angle and is effectively advected between columns as it comes down to represent the horizontal transport of the sunlight, direct beam of the sunlight. And then we also exchange, or diffuse, in fact, the up and downwelling diffuse fluxes in the two-stream scheme at the various points at which the radiation scheme progresses. So we're only adding an advection and diffusion. We're not adding extra streams or anything that's really complicated. But actually, despite the simplicity of this, it agrees quite well with a much more costly but accurate scheme. So what I'm showing here is a cumulonimbus over the Northern Territories of Australia. It's about 100 kilometers across, and the sun is at 60 degrees zenith angle. And so this is what the Mystique model from Munich calculates. You can see the shadows cast by this sort of cloud top here. This is what you would get in a 1D case, so it's totally featureless, right? So it just saturates and gives you a sort of grey image. You can't learn anything from that. And this is what my scheme gives you. So it's not quite the same, but it's pretty good, right? All I've done is sort of smooth out the radiation fields at appropriate moments, and you can capture the shadows, and in principle it's almost as fast as the original 1D. So if we could include 3D effects in our retrievals, then potentially we would enable a better interpretation of the key solar radiance measurements as part of the synergy of the satellite. So that's kind of thinking much further ahead. I'm going to have to whiz through a bit now. So one of the nice things we'll have for aerosol measurements is this high spectral resolution, so better distributions of extinction coefficient. We can actually do a pretty good job with this Aeolus satellite, originally for measuring winds. It's got fairly coarse vertical resolution, which we're going to be better at in the case of EarthCARE. This is an actual case of the Godzilla dust storm that came off Africa, and this is what Calypso saw, this big plume of dust. This is what Aeolus saw, so much coarser, but of course it's got this extra Rayleigh channel where it sees the molecular return, and you can see it's been attenuated by the dust, and the derivative of that with height gives you unambiguously the extinction coefficient. So from that, Mark Fielding has generated a sort of climatology of aerosol extinction. This is his derived aerosol optical depth. Now, of course, because of the coarse vertical resolution, you can't get too close to the surface. So it's down to 2 kilometers. And he's comparing this with 2 versions of the dust, of the aerosol that we use in the ECMWF model. We have a problem that our prognostic, this is actually, sorry, the prognostic scheme. We have a problem that all the aerosol disappears in the Southern Ocean for some reason, and this is very clear, the bias when you compare to the Aeolus values, and it's different from this other climatology we have. So this is just to illustrate the kind of data that we're going to get. So this is aerosol optical depths. It's only averaged as a function of latitude. And you can see, yes, the grey is showing the Aeolus measurements. And then our operational forecast of prognostic aerosol is shown here. And you can see there's particularly biases over the Southern Ocean. But this kind of information is going to be really crucial for evaluating these models. And we've had MODIS optical depths, but it's not vertically resolved. So this is kind of the game changer for aerosols. We're going to assimilate the data into our model. So this is how we're going to do it. Demonstrated it with CloudSat and Calypso. We're looking at a pole-to-pole slice. And what I'm showing here is a comparison of the observed radar reflectivity with what we simulate from the model, and likewise with the backscatter. So that's the observed and that's the model backscatter. This is going right through this nice tropical cyclone, which is shown here. And you can see, yeah, the model's quite good at getting the clouds in the right place, but you look in a bit more detail, and you can clearly see you've got biases and differences. And so the assimilation basically finds the initial state of the model that would give us a better fit to the observations through the 12-hour observation window. And then that will hopefully imply that the clouds are in a better place throughout the forecast. And in fact, we can demonstrate that. This is how we sort of score model forecasts. We do, in this case, 1 year of assimilating CloudSats and Calypso data. You can do this after the event. It wasn't available in near real time, but we can do this after the event and look at a change in the root mean squared error in temperature, the vector wind, and the geopotential height 6 days into the forecast. And you can see basically blue means that RMSE is reduced. So it's kind of good everywhere. If it's not, then it's not statistically significant. It's a fairly small improvement, 4%, but typically any single instrument gives you about that as a maximum impact. So for ECMWF, this is really important, actually, these kind of improvements in our forecast. So this is going to be really important. So the big thing now, of course, is everyone wants to run global cloud resolving model, and this is what models, and this is where we are at in the case of ECMWF. This is our model run on the European supercomputer LUMI. And this is simulated reflectance. I think this case is 4 kilometer resolution. We can actually run at 2.8, I think. And we're looking, there's an American computer we can run at 1.5, I think. You can see all kinds of features, and they look sort of amazing. It doesn't mean the model is right, of course. And if you look closer, you can see things like, you see the cloud popping up over land. Doesn't look quite realistic to me. So there's all kinds of ways in which we want to use the data to evaluate the high-resolution models. This is just to show one campaign we did in southern England, which highlighted how higher resolution doesn't necessarily mean higher accuracy. So here we scanned with this is the Chilbolton radar, which has got a very fine resolution because it's 25-meter dish. And so we scanned through lots of storms and analysed them statistically and compared them with the Met Office model run at different resolutions. Obviously, it wasn't global at that time, but it was we could run it 1.5 kilometres, 200 and 100 metres. And what I'm showing here is then how when we composite in this case, the vertical velocity, which we could estimate from the radar, with the between the radar, which is shown in black, and the various resolutions of models shown by the different colours. And this is for a case with showers, so we scan for a few hours. And this is a case with deep convection. And what we find, quite interestingly, is that obviously these cells are much too wide at 1 kilometre, 1.5, that's the red line here. And as you go to higher resolution, they get finer and finer. At about 200-metre resolution, the width of the cells is about right. But if you go to 100, they get too fine. So it goes through the scale at which it should. It doesn't converge in this case. And basically, there's still variables in these models that determine how large and intense the updrafts are. In this model particularly, the mixing length has to be prescribed, and that needs to be put in. So this just to highlight that, you know, high resolution doesn't mean always it converges to the truth. We still need to evaluate these from models, from our observations, and that's what we want to do with EarthCARE. The Doppler velocity is going to be super interesting. So this is the, we've only got simulations, of course, but this is a simulated Doppler velocity from this GEM high-resolution model and also the ECMWF model. And you can see the very big differences, right? The snow might fall at 1 or 2 meters a second between these two models. That's obviously going to be profound, or in this case, 3 or 4 meters a second for the rain. And of course, in the ECMWF model, we don't resolve the narrow updrafts we would get in convective cores. So this is really why EarthCARE Doppler is going to be a game changer, I think, for understanding, you know, full speeds and also updrafts and their scale. I'll have to skip over that in the interest of time. Well, let me just say one of the issues is that where you really want the updrafts, of course, the radar is going to be affected by attenuation and multiple scattering. So it may well be that we get updrafts only at the cloud top because we sort of have to throw away the bits deep in the cloud, and that's one of the issues with using 94 gigahertz. But yeah, so it won't be sort of telling you about updrafts everywhere, but hopefully there's something that can be useful for high resolution models. And I'm going to just skip now to this final slide, which is showing the potential of getting trends. This is showing one of Mark's papers with the trends in cloud top height, the height of high clouds measured by MODIS. And there's, I mean, the combined, we've got the 2 MODIS satellites in the morning and the afternoon, and the AMIP simulations, which tend to show cloud top height rising, which is a positive feedback. It means they emit at a colder temperature, and so that's acting as sort of a kind of greenhouse effect, if you like. And we can actually observe this now, and Mark showed this from MODIS, but it's interesting, my colleague Mark Fielding as well has found this from Calypso. So Calypso is shown here in the reddish color here, and that's, although we've got a much smaller sample of Calypso compared to MODIS that he analyzed, and there's a confounding effect of El Nino, of course. You can still get the sense of a bit of a trend. We probably need a little bit longer. One thing that's interesting is comparing to ERA-5, our reanalysis, we don't quite capture the trend in the northern and southern hemispheres, and this could well be because we didn't have prognostic ozone, and what happens is when the tropopause goes up, the tropospheric ozone goes down, it mixes away, and that effect has a radiative impact that may well sort of attenuate the tendency for the rising tropopause, but that's one theory, and I'd like to test that in ERA-6. We'll have prognostic ozone, and it will be interesting to look at the trends in that. So this is just highlighting that long periods of data, maybe not just using a single instrument, but combining CloudSat Calypso and then also EarthCARE will give us a longer time series. Now, homogenizing that time series will be a challenge, but in principle, we'll have longer periods to look at trends, not just in cloud top height, but also water contents potentially and reflectivities and all the properties we think that might be contributing to a feedback. So very keen on opportunities to work together to look at trends, to apply the same algorithms on the 2 different data sets and so on. So, summary of opportunities. Well, obviously the key thing, we've got everything on the same platform, and we're going to do the radiative closure to hopefully retrieve clouds that are consistent with the radiation we measure, and that's really important. I mean, I'm really keen on your ideas about how we can use this best to tackle the challenges of climate prediction. I've shown, some of the new information microphysically in terms of, particularly snow and rain measurements, but I'm sure there's other opportunities. And then these long-term products spanning the A-Train and EarthCARE. This called the multi-platform algorithm multi-instrument, multi-satellite algorithm analysis platform, I think. It's a shared computational resource, and there'll be a big announcement of that in a few months, I think, and it would be good to use that to work together. So, timeline for the next year. We're going to use the commissioning phase. When we've got real data, of course, there'll be lots of fixing of algorithms to be done, and that's totally normal. And then there's some campaigns starting. A major one is this orchestra campaign, large modeling component, and that will run from August to September this year. We'll release the data 6 months after launch from the level 1, that's the observations, and then after that we're going to move towards release of the level 2 retrievals after we've done the necessary sort of fixing of problems that we might find. And then there's the Living Planet Symposium is going to be a sort of major conference event in Vienna. It's sort of an ESA conference, and that'll be a great time to bring the community together. But hopefully we can have lots of other opportunities to bring in modelers and people from different continents to work together on using EarthCARE to tackle the challenges of climate science. I mean, they're as urgent as ever that we really try and address the issues of clouds and aerosols in climate models, and so hopefully EarthCARE is a key part of the answer. So I'll finish there. Sorry for overrunning a little bit, but thanks for your attention.
Okay, we have time for questions. Let's try to take some in the room. And if you have any online, put them in the chat and we'll read them out. Oh, and please come up and use the mic, otherwise people online can't hear you.
Okay, thank you. I have a question about your slide where you showed a 4% improvement in the forecasts with, I think it was CloudSat and Calypso data. Yeah. And my question is, have you or has anybody studied that quantitative improvement as a function of let's say a degraded instrument? So if CloudSat were half as sensitive or half as powerful, what would your RMS error be? Or if it were twice as good, what would it be? Because that sort of drives decisions about how much to invest in the cost of a system.
That's the kind of thing we could definitely do, yes. So often people want to, they come to us and say, we're going to launch a new satellite and we want to know what impact it will have on forecasts. And if it's totally new, this is a lot of work because you've got no basis for doing this analysis. In the case of CloudSat, EarthCARE, we've got CloudSat as a great test case. So, and now that we've got the setup, in principle, one could, I mean, the thing is that if you say half the sensitivity, you mean 3 dB less. So we're not going to miss a great deal, actually, in terms of the fraction of the area that has cloud in, reducing the sensitivity by 3 dB doesn't reduce the number of observation points by a great deal. So I imagine it wouldn't look a lot different from that. But certainly as you get to CubeSats where you might be looking at 10 or 20 dB less sensitive, then yes, indeed, you could do this analysis. We can't add sensitivity. We can certainly degrade it and look at the impact of that. We do need, we'd need a project that was funded to find the people to do the analysis. But if you wanted that to be done, it could be done, yeah.
Yeah, go ahead.
I need a qualification for something I didn't understand. You mentioned early on in your talk that you're using the Doppler to determine particle sizes, basically looking at the settling. And then later on, and we talked about the strong convective systems, you were using the Doppler to measure the vertical velocities in the clouds. If that's the case, is there some kind of transition place where you don't know what you're seeing? You don't know if you're seeing particle sizes, or you don't know if you're seeing vertical velocities?
That's absolutely right. So you can either take the approach, so it's exactly as you say, there's an ambiguity because you've got both the air motion and the fall of the particles through the air. So you can either do a retrieval approach where you say, I'm going to estimate the full speeds of the particles by using the reflectivity to estimate their full speed and then subtract that off from my measurements to work out what the air motion is. Or you could say, I'm going to forward model what the Doppler measurement is in my model, and I'm going to include the air motion and the full speed in my model to do that prediction, and then I compare in Doppler velocity space. But one assumption could be that particularly in cloud tops where we're going to get most of the measurements where they'll be affected by convective velocities, here the air motions are going to be quite a lot larger than the full speeds. I mean, if you're in the top of an ice cloud, it might be 0.5 meters a second, right? So And in this case, you might expect to get 5 or 10 meters a second at least of wind airspeed. So it is going to be a sort of marginal thing where we're going to have to do a lot of work and figure out how to do it. But yes, you have a point.
So now you're talking about using a model and a simulation to try to remove the ambiguity. What happens in the case of MCSs where the model doesn't have the MCS in the right location?
Well, I wasn't implying you would do a simulation. I was saying if you have a high you're right that an individual case might be challenging to compare to an individual case in a model, but you could in principle do this statistically, so look at the statistics. I mean, personally I agree with you in the sense that I think the main power of EarthCARE is going to be the velocities for the microphysical information. There's a really urgent need to know what the updraft speeds are, and it's not going to just pop out of the measurements. We're going to have to work hard to see how we can extract the information we need. But yeah, we'll do what we can. But yes, I agree, there's a limitation, yeah.
Thank you. So will there be any cloud classification products from the EarthCARE?
There will, and I can show you an example.
No, okay.
Yeah. So we're not classifying it in the traditional Luke Howard style sort of cumulus, stratocumulus, but we are interested in cloud phase, in precipitation type. So this is the one. So this is a case where there's different categories which are shown on the right-hand side. We're combining the radar, the lidar, and the temperature from the ECMWF model. And this is a case where we have, I can't really read it, but it's basically ice. This is ice where there's a possibility of it. So they have an ice versus snow classification. You don't have to use that. You just say, well, I'm just going to use ice and snow as one type. And then the key thing here is we've got ice or possibly snow, but we've also got supercooled liquid layer embedded within it. So we have a type for liquid coexisting with ice. Okay. We've got rain, we've got the melting layer, and we've got 2 different types of aerosol here. There's multiple other types that aren't retrieved in this case. So yes, this is our key product for that.
And this is combined both lidar and the radar together to do the classification, right?
Yeah.
Okay, thank you so much.
Yeah.
Can I ask you a quick question?
Go ahead.
So if you go to the slide in which you show the different resolutions of the models.
Yeah.
And I want to take a look again because...
Am I going the right way? No, I'm not. Yeah. This was the high resolution
Command Office stuff.
Yeah, yeah. There we go.
Yeah, that one. So let me look at, so the result is very interesting, but for me, if I look at the figures and I wouldn't be listening to what you were saying, which I was.
I went through everything too quickly.
I felt is that if there is a result that is interesting here is how bad the 1500 meter model is, right? Because it completely stands out compared to the others.
Well, it can't resolve updrafts because the effective resolution, as you imply, is coarser than 1.5. Yeah.
So if that's the main message, why? I mean, this plot actually shows that this obsession of going to 1 or 2 kilometers resolution is really not going to solve anything, right?
Well, it depends what you care about. You could say, well, it doesn't matter if I alias my convective cores to a little bit of a larger scale. What I care about is the rainfall predictive capabilities, time of day in particular, the diurnal cycle, but also the key thing is whether or not the cloud's organized properly, because often many of these models, one of the key things that we haven't been able to find is that even when high resolution, typically they don't combine to form MCSs when they should. They stay as isolated thunderstorms. That's not captured by this analysis.
No, I know, but I mean, so even if you go to the, let me ask you, sorry, I don't want to insist on this topic, but if you go to the animation, the very nice animation of the 4 kilometer.
This was the ECMWF.
Yeah, if you run the ECMWF, if you show the same thing with a 9 kilometer operational model, would you see any difference?
That would be 9 to...
This is 4, you said 4, right?
This is 4. The difference is
what would you see that is different on the frontal systems of the Hurricane?
The convection would be turned on at 9 kilometers and is almost entirely off at 4. So the diurnal...
No, but if you did this animation and you would show the 9 kilometer next to the 4, Do you think people will be able to see the difference?
That's a great question. I will ask my colleagues.
Because your 9
Yeah.
kilometers is so impressive that ECMWF runs in 9 kilometers, that I'm surprised that you're trying to sell what you're not doing and actually not highlighting the fact that you probably do as well as this with 9 kilometers. But anyway,
Yeah, I mean,
I'll stop
I'm not here to either. I'm not here to. I'm tending to agree with you. I mean, I know there's a lot of money in high-resolution models, and there are things that they can address better, like the diurnal cycle. But many problems lie with microphysics and things which don't converge at all because they're the same.
No, not at all.
And as I've showed, the size of the updraft certainly doesn't necessarily converge. So it's more the point that there's a lot of modelling out there, and there's a lot of people showing things like this, which almost is like a computer game. It looks great, right? That's all right. Job done.
The blue marble.
But for climate and for improving the accuracy, we need the observations and the rigorous testing. And so what I would really like to see is a formal framework to compare these models objectively against the same data sets, rather than people comparing their own models piecemeal in a way that favours their model.
Yeah.
And that's what we don't have. There's no international programme to do that. And I think that would be a crucial thing. And I hope EarthCARE could be one of the many observations that we would use to do that.
Absolutely. Thank you.
Any other questions? Luis?
So there was a slide about 3D scene reconstruction, and you went really quickly, and I'm just curious how does work and how do you test it?
So that's this one, yeah. Oh, it doesn't show. Maybe I have to go through the slide afresh. Technical guys, what's going on? I think if I stop the presentation and start it again, right, I'm sure that'll be enough. There we go, well, that'll do, right. So this is from Howard Barker's paper. He did the original thing, and then Xipeng Ku has applied it specifically to EarthCARE. Yes, so we have the different thermal and visible radiances from the MSI. And the idea is that you say, well, I'm off the main curtain of radar lidar retrievals, but I've got a combination of thermal and solar radiances that looks a bit like one on the curtain. So I'm going to extract that profile and insert it there. Okay? Now, this isn't perfect, of course, because you're not conserving the fact that clouds tend to be, you might get too much sudden change from one cloud to another if you take profiles from a very different place. But if you have a look at Howard Barker's original paper and also this one from Ku et al., then they've done an evaluation because they have the actual 3D scene underneath, so they can look at the radiative impact of the uncertainty in the reconstruction. So that has been evaluated. Yeah, that's a good point.
Any other questions? I'll ask one question. So as we were discussing earlier, it's really challenging to use these observations to improve model physics. I think you showed the most prominent example from CloudSat and Calypso, which is the cloud phase issue and the prevalence of supercooled liquid water. Yeah. When we look at EarthCARE, it superficially looks really similar to the A-train, right? But you did point out the new stuff is, for example, the Doppler, HSRL. If you were to look into your crystal ball, how do you think that this Doppler information is most likely to be used in a way that's going to actually improve the physics in ECMWF model or models more broadly? What is it? What's the key hook in the model that can be tuned or exploited to use this information?
So currently we have the full speeds are all rain is one type. So for a given rain rate, you have a velocity, and there's no way to have a different one for the same rain rate. All snow falls at 1 meter a second, and all ice clouds fall at 13 centimeters per second. Now, that's okay if you don't know anything, right? And part of the problem is that those full speeds are tuned to some extent, because if you increase the full speeds, it's a great way of changing the cloud cover, which often has biases. What I think we'll do is we'll see structures in the Doppler velocity that are quite obvious between particularly warm rain and rain coming from melting ice. And that'll just tell us that, in order to get the dynamics of those two different rain systems right, we need to add, for example, separate drizzle and rain types, or we need double moment. And we'll have the data to test it. I mean, the problem with, I don't want to be too critical, but there's lots of people who have a double moment scheme and they run it on cases and they show that the rainfall improves on one case. And it doesn't tell you anything statistically. You need to have observations over all the different cases that are of what you're actually simulating in the cloud, not just sort of rainfall that you can evaluate with NextRad. So and the rhyming example would be the equivalent one for snow, where if you've got snow at different heights and different amounts of supercooled water, you get different snow rates in principle. So the snow rates, which we cannot measure in any accuracy really at all from space, we have a hope of doing, I think, with EarthCARE, and that could be useful for things, people have said, oh, this would be useful for ice sheet dynamics if we knew how much snow was falling on them versus how much is melting. So, yeah, we need to engage with the modelers, but I do think there's potential, and I've got a few ideas that I've given you, but there must be more, yeah.
Great. Thanks. All right, let's give a round of applause.
Thank you.